Hello and welcome to another Sussex Universe lecture. Once again, I find myself in the strange position of introducing myself. So for those that do not know, I'm Will Roper. I'm a PhD student here in the Astro Department at the University of Sussex, and I'm also a member of the Sussex Universe team that organise these talks. But tonight I'm not only introducing myself, instead for tonight's talk I'm joined by Dr. Chris Lovell for a unique talk where we're going to try and show you how we use computers to model the evolution of galaxies in our universe. I'll now hand you over to Chris so that he can introduce himself and also introduce the talk.
Thanks, Will. Hello, and thanks for joining us for this talk on building a universe in a box. I'm Chris Lovell, a postdoc at the University of Hertfordshire, and with Will, I use simulations to answer questions about galaxy formation and evolution. In this talk, we hope to provide a quick introduction to these kinds of simulations, our motivation for using them, and the kinds of science that they allow us to do. When people think of a galaxy, they typically think of a grand spiral such as Andromeda on the left, or Messier 31 as it's also known. My personal favourite is Messier 64, or the Black Eye galaxy shown on the right, with these dark, thick dust lanes obscuring the visible light of the stars in the disk. Whilst these images from the Hubble Space Telescope are incredibly detailed, they are unfortunately just snapshots of these galaxies at a particular point in time. Galaxies evolve over timescales of billions of years, so we will never get to see a galaxy form and evolve, at least during a human lifetime. However, the universe does have a way of helping us out. The speed of light is finite, and whilst it's so quick that it's not noticeable in our day-to-day lives, over cosmic distances this becomes important. For example, the light from our sun takes approximately 8 minutes to get to us, so it's 8 minutes old by the time it reaches us. We are literally looking back in time, and over massive distances this becomes very useful, at least for astronomers. Right now, the latest space-based telescopes are able to peer back almost 13.5 billion years ago to when the very first stars and galaxies formed. So whilst we can't see a galaxy evolve, we can see galaxies throughout cosmic history at different points in their lifetimes. This is a bit like seeing a room full of people of different ages. If we were an alien that didn't know anything about people but was told how old each person was, the alien could perhaps infer some general ideas about aging based on the appearance and behavior of the people in the room, without knowing how each individual lived their lives in detail. But how do we connect the dots? How do we understand in detail how galaxies evolve given these snapshots? That's where simulations come in. We need simulations in order to understand how galaxies evolve over time and the processes that shape them. We can use our understanding of physics to build a model and compare this model universe to the real universe to evaluate how good a model it is. But our universe is very old, very large, contains 1 billion trillion stars at least, and is host to a zoo of spectacular and complicated processes and events. How do we build a universe in a computer?
Well, first off, before we build a universe in a computer, we need to actually know what ingredients we're going to need to do that. And this pie chart here shows that the 3 ingredients we're going to need quite nicely. So the first and possibly most obvious is the visible matter, so this tiny sliver here, this 5%. This is also known as baryonic matter, and it constitutes everything we can see. So that's every atom in the Earth, every human on Earth, every star in the sky, every gas atom wandering the cosmos, and every black hole gobbling up that gas. That is all only 5%. The other 95% of the universe is made up of dark components. The first of these, dark matter, makes up 85% of the actual matter in the universe. And this is an invisible form of matter that only acts through the gravitational force. Now, it always strikes me as a bit strange to say there's this thing, we don't know what it is, but we know exactly how it works. And the fact of the matter is we have lots of independent results that show us that is the best explanation we have right now for what we see, and also shows us how it affects baryonic matter, and we can fold that into our models. And we will dive further into dark matter's function shortly. The final component that makes up the vast majority of the universe is dark energy. Now this is an, again, unknown form of energy that drives the expansion of the universe. We won't touch in this talk much on dark energy. Beyond this slide, but it does appear implicitly in all the cosmological calculations that underpin our simulations. If you're interested in dark energy after this talk, I can highly recommend Professor Kathy Romer's talk from earlier this year called Will Dark Energy Destroy the Universe?, which can be found here on the Sussex Universe YouTube channel. So that's the what we need. We now need a how. And for that, we have to jump back to the 1940s. So there are many, many complicated processes going on in the universe, but the most important is likely gravity, and it's also one of the more simple. But it's in fact where we run into our first problem. So to calculate the gravitational attraction between a system of particles, you need to know the gravitational force between a single particle and all other particles in the system. This is called the n-body problem, and even for small systems it becomes basically impossible to calculate with a pen and paper. So we need to do this numerically, which means using a computer. The first of these n-body simulations was actually run using an early mechanical computer in 1940 by the Swedish astronomer Erik Holmberg. And he observed the fact that light intensity and gravity behave the same with increasing and decreasing distance, and used that to create an experiment that used light bulbs to simulate two galaxies evolving and colliding. His images from his paper are shown on the slide here. The dots here each represent a light bulb, and the different coloured dots represent the two galaxies that are colliding. And quite amazingly, from this really simple setup, he managed to show the formation of spiral arms, so that's what these lines are dictating here, and he also managed to show how orbital motion in galaxies will change during a galactic collision. But of course, we've come a long way since the 1940s, and even by the 1960s, supercomputers had come along, and they were capable of doing far larger calculations. An early example of an n-body simulation that was actually run using a supercomputer was run by the Swedish astronomer Lindblad, which I'm sure I've butchered the pronunciation of. And he ran it using the Swedish BESC supercomputer, which you can see in these images here. On the left is the control panel, so that's essentially the keyboard for the computer. And on the right is the memory, and it used drum memory, and it's considerably larger than a RAM stick you might find in your laptop or computer at home. Using this supercomputer, they took Holmberg's problem and they ran it on a supercomputer. And in fact, for a conference, they produced this animation, which I'll just show here. And what you can see is, as time is going on, the particles, they orbit, they begin to deform their orbits, and slowly you'll see spiral arms begin to form and then be destroyed, and then they'll reform. And this was a really big result at the time, and in fact, these high-density spiral arms are named after Lindblad for his discovery. But again, this is a very, very simple system. And of course, as time has passed, computers have become more powerful, and in fact the supercomputers of the 1960s are now dwarfed by even the common garden laptop, and our supercomputers are capable of absolutely immense calculations. This supercomputer pictured here is the Cosmos system at the University of Durham, and it's actually the supercomputer that was used to make many of the images and animations that you're going to see over the coming slides. So the question now is, what can we do? What can we do now with modern computing? And for that, I'm going to pass back over to Chris, who is going to tell you about the function of dark matter and show you what a modern supercomputer is capable of in terms of an n-body simulation.
We have already talked briefly about dark matter and how it interacts solely through gravity. Gravity is reasonably simple to solve if you have a computer, and if we do this, we find that dark matter arranges itself into this beautiful structure known as the cosmic web. In this video, we can see how matter, which starts off spread out quite uniformly throughout this box, quickly starts to cluster together and form this web-like structure, composed of nodes where huge amounts of dark matter collapses together, filaments that feed the nodes with new matter, and empty voids containing very little matter. Here are some example simulations using just dark matter. The images on the left show very detailed simulations of individual nodes of the web, known as halos, and you can see the rich substructure in these objects, where there is usually a large core of dark matter surrounded by lots of small substructures known as subhalos. The images on the right are simulations of much larger volumes, capturing millions, if not tens of millions of halos all evolving together. The biggest of these simulations cover a volume similar to that of the entire observable universe and help us understand this large-scale structure of the universe.
So now we have the skeleton down, but we need to start to add the baryons. And the fact of the matter is, baryons are messy. Much like the organs and nervous system of our own bodies, they may sit on a simple skeleton, but they themselves are very complicated. For baryons, slabs of gas crash together, stars form and die, explosions go off, heavier elements are formed, and black holes gobble up gas. And all of this needs to be taken into account. So let's talk about the various mechanisms we use to model these processes. The first of these is hydrodynamics. Most of the baryons in the universe are in the form of hydrogen gas, which behaves as a fluid. This means that we need to solve the fluid equations, and we need to take into account all the properties of a fluid, like pressure, temperature, the fact it can have multiple different phases. And of course, to exacerbate the complexity, all of these properties are dependent on its composition and the gas can cool. So to include gas and model its hydrodynamics, we must therefore solve the fluid equations, and worse, we need to do it efficiently so that we can simulate massive systems without the universe ending while we're waiting for them to finish. To do this, there are broadly two approaches. The first of these is called smooth particle hydrodynamics, or SPH, and uses particles to represent the fluid, and the fluid equations are then computed based on these fluid elements, the particles. The second method is called adaptive mesh refinement, or AMR. Astronomers tend to really like their acronyms. Instead of particles, this method uses a grid on which the hydrodynamics are computed. Now, both of these approaches have their pitfalls, but they both allow for the fluid equations to be solved both efficiently and accurately. Just to give some context, one example of a fluid interaction is shown here. These are Kelvin-Helmholtz instabilities, and it's what happens when two fluids moving at different velocities pass each other, and you get these little eddy currents. This particular example uses the grid AMR approach, and you can actually see the grid overlaid on the fluid. But just to point out, and maybe give this some more context, this isn't a phenomenon that is just happening inside cosmological simulations or in the depths of the universe. In fact, if you turn your head to the sky, you might see these exact same Kelvin-Helmholtz instabilities appearing in the sky and the clouds. So now that we've added gas to our skeleton, we need to take that gas and we need to form stars.
Stars are, of course, a crucial ingredient in a galaxy. Unfortunately, however, there are just too many stars in a galaxy to simulate them all individually. In our own Milky Way, there are approximately 200 billion stars. Even high-resolution studies of individual galaxies struggle to resolve this detail, and in large simulations of many galaxies together, this is currently beyond the capabilities of current supercomputers. Instead, we simplify the model by grouping together collections of stars into a single simulation element. This cluster of stars evolves together and provides a good estimate of the true underlying evolution of the individual stars. Stars are the nuclear engines of the universe, generating huge amounts of energy, as well as the heavy elements such as carbon and oxygen on which we are all made and depend on. These elements, as well as huge amounts of energy, get spread through the cosmos in supernovae, cataclysmic events at the end of a massive star's life. The image of Eta Carinae on the top right demonstrates the huge energy and matter outflows from such events. Over a whole galaxy, the combined feedback from multiple supernovae can combine to eject huge amounts of gas from a galaxy, as shown in Messier 82 on the bottom right. This simulation of a single galaxy shows how this feedback from supernovae impacts a galaxy's evolution. On the left, we can see the stars in the galaxy, showing the kind of image we would see with a telescope such as Hubble. The image on the right shows the gas in the galaxy, color-coded by temperature, where blue shows cold gas that can form stars, and yellow shows hot gas, where it is more difficult to form stars. You can also see from the bottom panels how gas gets thrown out of the disk into the surrounding space. Stars aren't the only things pumping lots of energy into a galaxy's gas. Every galaxy has a supermassive black hole at its center, billions of times more massive than our Sun. Recently, astronomers managed to capture an image of the supermassive black hole at the centre of Messier 87, shown at the top left. Black holes such as this gobble up nearby gas and spit it out at high speed, as illustrated by the artist's impression on the top right. These jets of gas can reach incredible distances, sometimes even larger than the galaxy itself. Centaurus A, shown at the bottom, is an example of a galaxy with an active supermassive black hole at its centre. The huge plumes of gas can be seen in X-rays and radio radiation. This can heat and expel gas from a galaxy in a similar way to feedback from supernovae, reducing the amount of cold gas available to form stars. This simulation shows feedback from a supermassive black hole blowing enormous bubbles of hot gas, which can not only stop stars forming within the galaxy, but also stop new cold gas from accreting onto the galaxy.
We now have all the ingredients and processes that we need to simulate the universe. And similarly to the dark matter only slide that Chris showed earlier in the talk, we can run these simulations across a whole range of scales. From the very high resolution simulations of single galaxies on the left here, to the absolutely massive simulations containing millions of galaxies shown on the right. And with these, we're really pushing the capabilities of modern computing. But earlier on in the talk, we said that one of the main strengths of simulations is they aren't just snapshots in time. So instead of looking at pictures, let's watch a small region of the universe evolve. Now in a moment, I'm going to start an animation which will show you a zoom into one of the more massive galaxies in the box. What you'll see is the stars represented by white light and the background colouring showing you the gas density. You'll see stars begin to form and you'll see this massive galaxy cannibalise its neighbouring galaxies as they fall towards it. And in some of these cases, you may see what's called a starburst, where the tidal forces pulling on that galaxy actually cause a huge amount of star formation before that galaxy finally falls in and gets eaten by the larger galaxy. Now this is of course very pretty, but with simulations we can visualize any property we like. For instance, here this is the exact same simulation, the exact same animation, but this time instead of showing the density of stars and gas, instead we're showing the temperature of the gas. And what you will see when I start the animation is small bubbles of gas at early times. This is the stellar feedback that Chris was talking about as stars are forming and dying. And then at later times you'll see these huge hot gas bubbles being expelled by the black hole in the centre of the galaxy.
So now we've put some flesh on the dark matter bones. But what do we actually see with a telescope? Unfortunately, we don't see the gas and stars directly. Instead, we observe the electromagnetic radiation initially generated by stars and black holes that, once emitted, interacts with the gas and dust within and surrounding the galaxy. If we want to understand our observations of galaxies and learn about the underlying processes occurring, we need to understand and model how this light is generated and its interactions. This requires another step in our simulation pipeline. This step is known as forward modeling and is the final step to go from intrinsic properties to mock observables. The images on the right show simulated galaxies modeled to replicate observations. At the top left is a spiral galaxy observed in the ultraviolet range of the spectrum, which tends to trace young, massive, newly formed stars. The image on the far right shows a simulated galaxy imaged in the optical. This light tends to trace the majority of the stars, but is obscured by dust lanes in the galaxy, as you can see. In contrast, the image at the bottom in purple shows the emission at far infrared wavelengths. At these wavelengths, it is the emission from the dust that is visible, rather than the stars, and provides a different perspective on the galaxy. By comparing the simulations and observations at different wavelengths, we can better understand the details of how galaxies are evolving.
We can then take this a step further and use simulations to predict what could be visible to upcoming observatories such as the Webb Space Telescope, which now finally, after many delays, is due for launch in under a year in October 2021. When Webb eventually launches, it will revolutionise our understanding of the early universe. But to fully understand its capabilities before it launches and to interpret its eventual results, we can use simulations to make predictions such as the one shown here. This shows a galaxy 13.5 billion years ago in a simulation, including the noise that's inherent within Webb's instruments. Now, these sorts of images are important because when we're planning surveys, we have a particular science goal in mind or a question we want to answer, and we need to know if Webb is capable of producing the observations that answer that question. But this goes both ways. If we predict a galaxy should look and have properties like they do in these images, but when Webb eventually sends back its results, we see something completely different, we know that something is wrong within our models, or indeed missing. And of course, we already know that there is much missing, and a lot of future work on simulations is looking to fill these gaps. These gaps include magnetic fields, extremely energetic photons called cosmic rays, explicitly modelling the effects of radiation in a process called radiative transfer, and cosmic dust production. But beyond simply adding these elements, we are also constantly utilising advancements in computing to simulate larger and larger volumes with higher and higher resolution. And hopefully this will lead to a better understanding of our universe as a whole. So that's all, folks. We hope that you've enjoyed this talk. We hope that you walk away understanding how to build a universe in a box. And we'd just like to end on thanking a few people without which we wouldn't be able to produce this talk. Firstly, our supervisors, Peter Thomas and Stephen Wilkins at Sussex. Chris has now moved on to pastures new, but we were both supervised by the same people at Sussex. And then the Swift team, and particularly Josh Borrow, who helped massively in the production of the animations that we've shown here. And the Eagle team, who without which we really wouldn't have research to do. A lot of what I do anyway is underpinned by the work they did in recent years. And of course, there are many more that we can't physically list here. So we'd like to thank all the people around the world that have been involved in the production of the beautiful images and animations we've been able to present to tell you this story of how we do the work we do. And remember, if you're watching live, the Zoom Q&A is about to start at the Zoom link in the description down below. And please do join us for any future talks. Thank you very much.